now turn our attention to the calculus of vector functions. So having set the foundation for what a vector function is and some of the algebraic operations and properties that are associated with these vector functions, we now turn our attention to calculus. And by calculus, essentially, this is really these are the topics that we're going to look at. I would say somewhat briefly, but still, I would say, comprehensively. It's not like we're going to just kind of gloss over any of these concepts. But basically, what we want to be able to think about is continuity of vector functions, limits of vector functions, derivatives of vector functions, and then finally, you might guess it, integrals, both definite and indefinite, of these vector functions. Right? When you kind of think about it, this pretty much is what your first 2 semesters of calculus is really about, going back to continuity and limits and so forth. Well, what we're going to focus on now is just the how of all of these. Like, what does it mean for a vector function to be continuous, or what does it mean to find the limit of a vector function? What does it mean, or how do we find the limit or derivative, or maybe first or second or third derivative of a vector function? And similarly, how do we integrate them? In subsequent videos, we're going to talk about what the derivative might represent and what the integral might represent. And it might not be what you think, right? So let's start with the how now, and then we'll talk about the why later. So as far as now, typically, we're supposed to do limits before we do continuity, so it doesn't really matter. I mean, having a notion of what all these things mean, the order doesn't make much difference, but I guess to be consistent with the way the material was presented in the single variable calculus class, well, let's do it that way. So let's start with the limit, and what I'm going to do is I'm not going to provide any formal proofs, because the proofs, for instance, of like continuity and the limit definition of the derivative and so forth, it looks exactly the same, and then we simply switch on over to our rules and so forth. Same thing with integrals. The way we define an integral will be pretty similar. So I'm literally just going to state how we compute these things and then do some examples. So let's start with limits, right? So I will write all the rules in green, and let's state the rules in terms of a spatial vector function. So a vector function in R3, and again, the definition or the property or the process will be identical or very similar, really, to a planar vector function, just by eliminating what's in the third component. So let's say we have a vector function f of t, g of t, h of t. Then if we want to compute the limit as x, or not x, it'll be t now, right? So we have to get used to that. The limit as t approaches a number of this vector function. Well, how is it computed? Well, it's like we would have 3 limit questions in one. We would have to find the limit, hopefully if it exists, of the first component, so that's f of t as x approaches a, and then we would find the limit as t approaches of the middle component, and then the limit of the third component. And provided they all exist, right, then the limit of this vector function would be another vector that has components being the respective limits of f, g, and h, right? So I'll just say provided each component exists. If at least one of these components does not exist, then the overall limit of the vector function will not exist. So we'll just say provided each component exists. Right? So in a nutshell, what we do is, what this means is we compute limits component wise, right? So we do it per component, and hopefully they will exist, right? Okay, so let's do an example of a limit. So I'll write it. So let's say we want to compute the limit as t approaches 1 of, and I'll just write the vector function down. Let's say we have t cubed minus 4t plus 4 in our first component, and then the second component, let's say we have the sine of 3t minus 3 over, let's say, t minus 1, and then let's say we have the third component be e to the t minus 1 plus the square root of t squared plus 1. Right? So that's our vector function. Several different types of functions involved. So what this property is saying about the limits is that the limit of this vector function is equal to the vector function comprised of these components. So the limit of t cubed minus 4t plus 4, comma, the limit, again, and they're all as t approaches 1, of, in this case, the sine of 3t minus 3 over t minus 1, and then the limit as t approaches 1 of e to the t minus 1 plus the square root of t squared plus 1. So we have to evaluate each of these separately. Well, let's, let me see here. Yeah, let's kind of do these off to the side. So the first one, if I have to find the limit of that polynomial, right, process-wise, if we recognize that the function is continuous at t equals 1, then the limit is simply a function evaluation. And polynomials, we know, are continuous everywhere. In fact, we're going to get to continuity in a second. But process-wise, this is equal to 1 cubed minus 4 times 1 plus 4. So that is equal to 1. So the limit of the first component of my vector function exists, and it's equal to 1, so that's good. Let's look at the second component. So we have the limit as t approaches 1 of the sine of 3t minus 3 in parentheses over t minus 1. Now, when we try to evaluate this by simply plugging in t equals 1, see what happens is the limit as t approaches 1 of the numerator, the sine function, well, this is going to give me the sine of 0, which is 0, and then the limit of the bottom as t approaches 1, so the limit of t minus 1 as t approaches 1, that's also 0. So right, we actually have an indeterminate form. So this is the undesired indeterminate form. And there are different ways you could do this. Probably the most common way now, now that you've evaluated limits several times, is by using L'Hopital's. So using L'Hopital's, we take the derivative of the top, right? And essentially what we're going to do is replace this limit with hopefully a simpler limit, one that is not indeterminate. So the derivative of the top, that's going to be 3 cosine of 3t minus 3 over, and then the derivative of the bottom is 1. So now we know for a fact that this is not indeterminate. We have to get a number out of this. And if we plug 1 in, what do we get? We end up with 3 times the cosine of 0 over 1, which is equal to 3. So the second component, that limit also exists. And then finally, we can compute the limit of the third component. So the limit as t approaches 1 of e to the t minus 1 plus the square root of t squared plus 1. Well, again, our exponential function, even though it's composed with a polynomial, it's still always continuous. This square root function, sometimes we have to be careful with the square root, but under the square root, we have an expression that is never negative, right? So it's never negative. So this component is always continuous. So yeah, we can just plug t equals 1 in, and we will have e to the 0 plus the square root of 1 plus 1. So that's 1 plus the square root of 2. So our answer, right? So we got that the first component approaches 1. The second component approaches 3. And then the third component approaches 1 plus the square root of 2. Now, what exactly could this look like? Now, remember, our vector functions, whether they're 2D or 3D, they can represent a curve, right? I'm not necessarily going to focus on the curve point here, but let's say, and this would be a 3D problem. So let me do this. So what's happening is as t gets closer and closer to 1, we're really asking what number does each component get closer and closer to. So basically, so this vector here, 1, 3, 1 plus the square root of 2, I am going to draw that kind of as a dotted vector. So this is the vector 1, 3 plus root 2, 1 plus root 2. And then the limit, so this vector here, and the reason why I draw it as a dotted vector is it's to say that the vectors that are defined by this function are going to be getting closer and closer to this one, but not actually equal. So it's a matter of, let's say you start by plugging in something like t equals 1.1. Maybe you'll get this vector. And then if you plug t equals 1.01, you might get another vector like this. And then remember, all these vectors, they start at the origin. So you get essentially a sequence of vectors, and as your t gets closer and closer to 1, these vectors all get closer and closer to this 1.3, or I'm sorry, 1 comma 3 comma 1 plus the square root of 2. So it's essentially, it's a limit of vectors that we're looking at. So as t gets closer and closer to 1, this vector function produces vectors that are closer and closer to 1, 3, 1 plus root 2. Now, again, another reason why I have it dotted is, remember, the middle component of this vector function gave us something indeterminate. So note that if this is our r of t, note that the middle component is not defined at t equals 1, but its component, right, or its value approaches 3 as t gets closer and closer and closer to 1. So that's another reason why I have this vector here sort of being dotted, right? So geometrically, that's kind of what the one way you can interpret the limit of these vector functions, right? So that's limits. So continuity, right? So let's write down the property for continuity. So again, here's our vector function f of t, g of t, h of t. So this vector function is continuous for all values of t such that f, g, and h are all continuous. So in other words, if you're given a vector function and you're asked to determine, its continuity, where is this vector function continuous, right? Assuming, again, our t it represents could possibly represent all real numbers, right? What values for what subset of real numbers are all or is all three components of the vector function continuous, right? So we essentially, again, it's like you're doing a continuity problem, but 3 times over or 2 times over, depending on whether the vector function is in R2 or R3, right? So again, we're going to look at each component, look at the continuity of each, and then see what values of t make all 3 components continuous. So let's look at an example of this, right? State, so the question might be worded like this: state the domain of continuity for, and let's say here is our vector function. I'll use the ijk notation. So let's say we have t over t plus 3. Let's say we have inverse sine of 2t minus 1. And then let's say we have the square root of 4 minus 3t, right? So let me put angled brackets here. So there's our vector function, and we have to determine the domain on which this function is continuous, right? So let's go component by component. So if I call this f of t, so f of t equals t over t plus 3, well, this is a rational function, and we know that rational functions are continuous whenever their their denominator is never 0. So this function is continuous when t plus 3 is not equal to 0. That's the same as saying t is not equal to -3. All right, good. Let's move to the middle component. I'll call that g. Now, these, your inverse sine and inverse cosine functions, you probably discuss these functions the least, with respect to continuity, but I'll remind you what the property is. So this function is continuous when the inner function, so notice that this is a composition between an inverse sine, your arc sine, and a linear function, 2t minus 1. Well, the arc sine and also arc cosine, these functions are continuous whenever the inner function is strictly between -1 and +1 inclusive. So that means 2t minus 1 must be strictly less than 1, or less than or equal to 1, and strictly greater than or equal to -1. So whatever the inner part is, whatever you're taking the arc sine of, that expression must be between plus or minus 1. And then we can go ahead and isolate t. So let's add 1 to each part of this compound inequality. So we'll have 0, 2t, and 2, and then divide each part of the inequality by 2. So we will have 0 is less than or equal to t is less than or equal to 1. Okay, so we have that. And then finally, we have a square root function. So let's call that our h of t. So that component, the square root of 4 minus 3t, is continuous when, now for an even root, like a square root, a fourth root, sixth root, and so forth, when working with real numbers, we can only take an even root of a non-negative expression. So what's under the square root has to be greater than or equal to 0. So the 4 minus 3t must be greater than or equal to 0. Let's go ahead and isolate t. So subtract 4 and then divide by -3. And oh, I think I flipped my inequality a little too soon. So by subtracting 4, the inequality is pointing in the same direction, but now when we divide by -3, that's when we flip it. So t is less than or equal to -4 over -3, or 4/3. So we basically have to write down the set that satisfies all three inequalities, right? So t not when t not equal to -3, that's already satisfied by this, right? And also t less than or equal to 4/3, that's also satisfied by this. So essentially, if you were to think of these as intervals, so if you wrote these using your interval notation, this one would look like this, right? So just take out the -3. This one would simply look like this using the square brackets, right, for the interval notation. And then this one would be this, so 4/3, like that. And then essentially your final answer is what is the intersection of these three sets? Where do these three intervals all overlap? What do they have in common? Well, this interval is actually a subset of this interval, and so it's also a subset of this interval. So essentially, let's write this down. So this is what they have in common. So r of t, so therefore r of t is continuous for, again, you can write either one. I for some reason I like to use the inequality, but you can certainly express it using the interval notation, right? So this function, if we were to graph it and we tried to define the range for our parameter t, only this range will produce a well-defined and nice continuous function. All right. Okay, so that's continuity. Next up, derivatives, right? So again, let's write down what the rule is. So if we have a vector function, again, I'll do the 3D case. So if r of t is defined by this vector function, and if f, g, and h are differentiable on some common interval, so and f, g, and h are differentiable on some common interval, kind of like how we found that common interval, but here we're looking for not just continuity, we're looking for differentiability. So in some common interval, then, well, how do we compute the derivative? Now, as far as the notation for the derivative, we can use our famous prime notation, or we can actually use the Leibniz notation. This is what it looks like if we use our d, right? So we make sure that we indicate that there is a vector there, and we're using our same differential notation d over dt, where we can use our r prime. But the nice thing is, again, as long as each component is differentiable, to compute the actual derivative of the vector function, we take the derivative of each component, right? I mean, if you love derivatives, then you're going to love differentiating vector functions, because it's either 2 or 3 derivatives in one problem, right? So again, the derivative is evaluated component-wise. So let's look at an example of this. All right, so let's say, let r of t be the vector e to the -2t, and let's say the square root of 1 plus t, and then let's say the sine of t squared. Right, so there we go. So again, I just picked a few different types of functions and defined each component by those functions. And let's go ahead and compute the first and second derivatives, right? Because again, once we have a handle on differentiating once, we know it's a process that we can repeatedly perform. So let's write down the first derivative of this vector function. So in all three cases, we are going to have to use the chain rule, right? Because they all represent some kind of composite. For the middle component, as usual, we will think of it as 1 plus t to the 1/2, right? All the other composites are pretty clearly written. So using our chain rule, the derivative of the first component is -2 e to the -2t. The derivative of the second component is 1/2 1 plus t to the -1/2, and technically we're supposed to multiply by the derivative of the inside, which is 1, so I'll write that there just as a reminder that we are using the chain rule. And then here we using our chain rule again, the derivative of sine is the cosine, and then it's of keep the inner function, and then I have to multiply by the derivative of the inner function, so we get our 2t, right? So that's our first derivative. Let's say we had to differentiate it a second time. So r double prime, that's equal to, let's see, and so a chain rule again, along with our constant multiple rule. This is going to give me 4e to the -2t. Differentiating the middle component again, so this is power and chain rule again, so -1/4 1 plus t to the -3/2 again times 1. Now here we need our product and chain rules, because even though like in the first two components we just ended up multiplying by constants, but now we're multiplying by 2t, which is another function. So using our product rule, we will have negative sine of t squared times 2t. So that's the derivative of the first. But so this part alone is the derivative of the first, right? Because I have to use the chain rule again, but then I have to multiply by the second. So that's my 2t. And then plus the first, which is the cosine of t squared, times the derivative of the second, which is 2, right? And I just prefer to do the product rule in that way. You may like to start with the first times the derivative of the second, and then add the derivative of the first times the second. It works out to be the same because the operation there is addition, which is commutative, right? So let's simplify this. And we have 4e to the -2t, and then so if you want to write this, in the nice form with roots and obviously no negative exponents, you'd end up getting a -1/4 times the square root of 1 plus t to the third power, right? So that's the middle component. And then the third component, let's see, since this term is positive, let's write that one first. So it's 2 cosine of t squared, and then here we have a -4t squared times the sine of t squared. So -4t squared times the sine of t squared, right? And then close our vector. So that's the second derivative of this vector function. Again, going forward, we'll see what these vectors represent, but for now we just want to focus on the calculation, right? And then lastly, of course, what we have left is integrals, right? So let's state how we compute the integral or antiderivative of a vector function. So, and in fact, I'll state both the indefinite and the definite integral in this particular property. So if r of t is equal to f of t, g of t, h of t, where f, g, and h are integrable. Now, we don't really talk too much about integrability, certainly not as much as we do differentiability, but it basically says that when you go through and you do your constructions with your Riemann sums and you take the limit of those Riemann sums, then those limits always converge, right, to a nice finite number, right? So if those functions are integrable, then so what notation do we have for the indefinite integral? Well, we use the same integral sign, and then we have our vector function there, and we still use our dt. And basically, you would end up forming a new vector function by taking the antiderivative of each component. So it's the antiderivative of f of t dt, comma, the antiderivative of g of t dt, comma, the antiderivative of h of t dt. And you will still have a constant. Now, what you could do is you could write each component with their own constant. So after you integrate, you'd have like a plus c1 there, and then a plus c2 there, and a plus c3 there. But what you can do is you can group those constants in their own vector and just put it at the end and say that this is plus a vector constant. So we'll still use the letter C, but now we will indicate that it's a vector by, again, putting that little harpoon over it. So this is our vector constant of integration, right? Again, so when we integrate just a scalar function, like a f of x, we will get a scalar constant of integration. When we integrate a vector function, we get a vector constant of integration. And then let's say we have a definite integral that we have to compute. It's very, very similar. We just put the limits on each of these three integral signs. And of course, we know that for definite integrals, there is no plus c, right? So this is the integral from a to b of f of t dt, the integral from a to b of g of t dt, and the integral from a to b of h of t dt, right? And this is going to be a number, right? So let's do one example just to kind of wrap this up, and I'll use the same function. So let's say we have an example. So let r of t be equal to, let's say, the vector function t squared, comma, e to the 3t, and then the sine of pi t, right? So let's say we have that. So let's first do an antiderivative of this. So let's find the antiderivative of this vector function. And I'll write this in two ways so you can see how you can do it. But essentially what it is it's a vector where you integrate each component separately. And that's kind of the theme when you're doing the calculus of these vector functions, right? You do whatever the operation is, you do it per component. So let's say we were to write down individual constants of integrations or integration for each of these. This is what it would look like. The first component, using our power rule for antiderivatives, is 1/3 t cubed, and then it would have a c1. And then using our exponential rule here, this will be 1/3 e to the 3t plus c2, again, its own constant of integration. And then the third component will be negative 1/pi cosine of pi t plus c3, again, its own constant. And here you really, if you're using this notation, you really want to indicate that these are different constants. But that's fine. But here's another way it can be written. Since the constant is just added on to each of the, I would say like the base antiderivatives, if you will, we can actually separate them and express this as the sum of two vectors. So actually do a little bit of vector algebra and say this. We have 1/3 t cubed, 1/3 e to the 3t, and negative 1 over pi cosine of pi t. So keep essentially the terms that are functional in one vector, and then plus my vector of constant, c1, comma c2, comma c3. And then this is what we would now refer to our vector constant of integration. So this is typically how you might see it written. You'll have your 1/3 t cubed, 1/3 e to the 3t, and negative 1 over pi cosine of pi t, and then plus your vector constant, right? Okay, so that's the antiderivative. Now let's say we had to integrate this from 0 to 1, right? So if we had to integrate from 0 to 1, then we would basically, so I'm going to go back through. So now what we would have is like start kind of the setup. This is how it would look, right? You would take the definite integral of each component, in this case from 0 to 1. So 0 to 1, e to the 3t dt, and the integral from 0 to 1 sine of pi t dt. But so I'm not going to write all the other things, but once we recognize what the antiderivative is, right, which would be this, and remember for definite integrals we don't need a plus c, what we can do is we could say, well, it's simply, here's our antiderivative. So I'll write down what I have on this last line. Right, so do that, and then minus 1 over pi cosine of pi t, and then use that same vertical line that we know that we're going to now evaluate this vector or this antiderivative at 1 and at 0, and guess what? Our fundamental theorem of calculus still holds, right? So at the upper limit, we'll have the vector 1/3, 1/3, 1/3 there, and then 1/3 e to the third, and then the cosine of pi is negative 1, so I'll end up with a positive 1 over pi, and then minus, at the upper limit, what do we have? Well, the first component is 0, second component is 1/3, cosine of 0 is 1, so I end up having a negative 1 over pi there, and then do our vector algebra and subtract these two vectors. So our answer is going to be a vector. So we have 1/3 minus 0, comma, 1/3 e cubed minus 1/3, and then 1 over pi minus negative 1 over pi. That gives us 2 over pi. And that's the value of this definite integral. Now, what does this mean? Well, this is where, this is like the cliffhanger. So you're going to have to tune into the next episode or maybe the next few episodes to figure out what this vector might mean after, integrating or finding the definite integral of a vector function. So since I know you can't wait, again, I'll look forward to seeing you in the next video. See you then.